right, so I've got a combined system here. I've got steam going through from 1, then through a turbine to 2, then through a heat exchanger to 3, then to another turbine to 4. And I've got a separate stream of air going from 5 through that heat exchanger all the way to state 6. And I'm told that it's steady state, I can ignore kinetic and potential energy changes, and that heat transfer is negligible between the working fluid and the surroundings. So I need to find T3, and I need to find the power output for that second turbine. So for T3, well, if I look at state 3, I know one property, and I need to know 2 in order to fix it, 2 independent intensive properties. So my intensive property list, I've got temperature, pressure, quality if it's applicable, specific volume, internal energy, and enthalpy. And enthalpy is the thing that I could probably get my hands on. So if I find H3 for water, I can find the temperature T3 at P3 and the H3 value. So in order to do that, I'm going to apply my energy balance, and I'm going to apply it to that heat exchanger. And the way that I draw my control volume, I don't have any heat transfer crossing that purple dotted line, crossing that system boundary. And so if I apply my conservation of energy for an open system, everything is going to go away except the m dot h's in and out. So with that being said, now I can say, okay, well, I've got things going in at 2 and 5 and things going out at 3 and 6. And I've color-coded things so that the water is represented with blue, the red is represented with the red represents the air. And then I just solve for H3. So let's start with those H values, see if I can get those. So for the air, for state 5, I know T5, it's 1500 Kelvin, so I can get the H5 value. And I know T6, so I can get the H6 value. H2, of course, is associated with water. That's the enthalpy of the water at state 2. And I know the temperature and I know the pressure, and that's enough to fix my state. I find out that I'm superheated, so I go to table A4, which is my superheated tables, and pull off that H2 value. The m dot of my air, well, if I do a conservation of mass between 5 and 6 to that little squiggly, the red squiggly there, I'll see that m dot 5 and m dot 6 are equal to one another, and I'm just going to recall that m dot of the air. Now the m dot of the water, if I do a conservation, apply my conservation of mass to the turbine, to either one of those turbine 1 or turbine 2, or to just the water within that heat exchanger, just that blue squiggly, I'll see that m dot 1, m dot 2, m dot 3, m dot 4, they're all equal to one another, and I'm just going to recall that m dot w. And well, I need to find out what m dot w is. And if I look at my diagram here, the only thing that will tell me about the rate of things happening associated with the water is the power output for the first turbine. So what I'm going to do is I'm going to apply my first law to the turbine, to the first turbine. And here's my first law. I know lots of things going to go away. dE dt goes away because it's steady state. Q dot goes away because that's one of the typical assumptions that we make for turbines. And the problem tells us that we can ignore heat transfer with the surroundings. The W dot, of course, does not go away, but the potential and kinetic energy changes do from the inlet to the outlet. And so this is all I'm left with. The sum of the m dot h's going in minus the sum of the m dot h's going out is equal to the power output of the turbine. That's m dot w h1 minus m dot w h2. I know the power output of the turbine. And so I can rearrange this to solve for m dot w. And let's see, I've got W dot, and that should not be a big W, that should be a W dot. But big W dot T1, which is the 10,000 kilowatts, and then H1, well, I've got enough information. I've got T1 and P1. It's also superheated, I find. And now I just plug and chug, and I get a mass flow rate of 23.46 kilograms per second. All right, so I've solved for my H3, and now I've got the other intensive property that I need to fix my state at state 3 and find that T3. So it also ends up being superheated. I do need to interpolate for that temperature, but otherwise I'm done. And now I'm ready to move on to part B. So I've kind of pushed my properties over to the other side just to give myself a little room. So I'm trying to find the power output of the second turbine. And if I apply my energy balance to turbine 2, I see that the W dot for the turbine 2 is equal to the sum of the M dot H is coming in minus the sum of the M dot H is going out. So I've got things coming in at 3, things going out at 4, and let's see, now I know M dot W. I don't know H3 or H4. Oh, wait. I do know H3 because I just solved for it. And H4, I've got the temperature and I've got the pressure, and that's enough to fix my state. It also ends up being superheated, so I can look that up in table A4 and solve for the power output for that second turbine. So power output for the second turbine ends up being 16,213 kilowatts. So, all right, well, we're done. Hope that was helpful. Thank you for watching, and let me know if you have any questions.